warping. Okay, right? Warping issue. Okay, so we have last time that you saw. We have the beam. Okay. So beam. Drawing class. Okay. Alright. Beam. And then once it is it's not focus. Once it is subjected to torsion. So when we have torsion applied, you are sort of producing this force couple in the cross section, right? Because you apply the moment, so okay, this is happening in there. So from this, essentially you are trying to make the beam deform. So okay, let me twist it again. Like this. Right. So this stick out. Okay. This side comes out and another side just stick in. In the contrary, the thing here will be difficult to draw. Sort of like this, right? So this is warping. So if you consider a cross section of the beam, under warping phenomena, so when it warps, okay, top go to one side, whereas the bottom move literally to the opposite side, okay, which cause some sort of thing like this. Okay. center line. Here, this is just the cross section, okay, during the warping. This is the 3D view, such that you can see that two sides are moving in and moving out. Okay, this, okay, just cut the cross section so you'll be seeing something like this. So this angle, last time it was defined to be the phi. Okay. So as this is defined this way, h over 2 and h over 2, the depth. So this just go to the center of the flange. Depth approximately. So the displacement, okay, lateral displacement, horizontal one. So we measure it from center here to this here. Likewise for the bottom one. So this is your U, horizontal displacement. So the relationships between the U and phi under small deformation, you can express that U is equals to phi h over 2, right? Where U is phi is in radian unit, so you end up with the U. Once you end up with the U, okay, as you see that I wrote here, okay, you'll be having force. This force is the shear force, right? You can just disregard the web, because the web compared to the flange, web is nothing in this direction. Okay, web is so small, and in this direction the stiffness of the flange part is huge. So web will be neglected under this consideration, okay, under this derivation. Now, okay, you can see that your flange under this lateral motion, it will produce shear force. Okay, but this shear force will be the function of U. It's not a function of V. Alright? This is a beam. Support here, the load apply this direction. You apply load, you get this deformed shape. This shear is mainly carried by the web. But the shear we are talking about is a shear when you have warping. So warping is coming with the lateral torsional buckling. So you come down like this is the V. Okay, it's not the part we are considering. We are considering the part that it comes down and then it goes whoop, like this. Okay, so when it goes laterally like this, we are just looking at it at the top view and see the side or lateral displacement U, which is this one here. So it go into the side. This is the plane of your flange. Your flange will be under this sort of flexure. Okay, so it is a stiff axis of the flange. So we are talking about I subscript Y of flange. Right? IY flange, what is it? It is simply just, if you refer to this picture, you'll be having just the flange. One flange, okay, alone. And then you take this is y-axis, right? Last time I used Y or C. Y. C. I use C, right? Okay, okay. Sorry. So it has to be the C to be consistent with last time derivation. Okay, this is the C axis. Okay. So this is the C vertical axis. So we are talking about the bending, about this C-axis. So this what is it? Precisely, IC flange. If you have this as a flange width being the BF, not boyfriend, okay? B is the width. Subscript F is a flange, okay. And then this is the T subscript F, thickness of the flange, okay. So IC flange will be equals to 1 over 12, right? T subscript F and B subscript F cube. Okay, the moment of inertia of the rectangular cross section. Then, if you want to find the moment which is associated with the warping, moment associated with warping, then you will be getting to shear force couple. All right. The shear force couple. That will be the top and bottom flange shear multiplied by the moment arm, which is H. Okay. In order to find the shear, this is the U, right? Displacement U out of this plane. So you take the third derivative of this U with respect to, we define X along the axis, right? Last time with X is along the axis, but U is this side lateral motion, right?
Y.
And you what use what?
U is the Y axis.
U is the along the X or in
Y.
In Y, or and C is in there, all right, and then the V is in the C, U is along the Y. Okay, so make sense. Then du dx cube. Okay, so it is consistent. This is the shear, not yet, right? To make it shear, it must be the EI. But this is the IC flange. Alright. To get bending, you just use the EI second derivative of U with respect to X. To get the shear, it turns out to be third derivative. Okay. E will be just E, still E. I will be the TFI. Keep in mind that this is only one flange. Okay. So now you get shear force. Alright. The shear force, you multiply it with what? H, right? With H, the total H. So this pair, okay, of force produce the moment, then multiply by H. Okay. We transform it a little bit by, we have E, we have IC flange, we have third derivative of U, which is represented by phi H over 2. So the third derivative of phi with the x cubed multiplied by H over 2 and multiplied by H back there, right? This is that H. So turns out we have, and then I substitute terms like E, nothing to substitute, but I have 112 there, TF, BF, Q, okay, H square over 2 there, and then the third derivative with x cubed finally we have the E times TF BF Q H square over 24, third derivative of B x cubed this is C subscript W. So now you get this warping constant. This is what I owe you last time. How do you get this? Okay, all right. Well, so last time we derived the formula for the buckling, lateral torsional buckling of the beam. So let's take a look at the beam curve. So this horizontal axis is the LB. The vertical axis is the moment, which is the M subscript CR, critical moment. So the failure of the beam with the bearing LB, which is the unbraced length. Okay, the segment is unbraced. So first of all, you have something pretty much like the column. Okay, so you'll be having the elastic buckling, and then in elastic lateral torsional buckling, and then you'll be able to develop the, when the LB is super short, you'll be able to develop the plastic moment. Okay, so you have 3 steps. First of all, this part, this is equals to MP, plastic moment. The plastic moment you derive in months, 2 months ago, okay, that plastic moment. So this is the LP, okay. So when your LB is less than LP, then you can develop the full capacity of cross section at plastic moment. Somewhere over here, elastic LTB, okay, lateral torsional buckling. And then the connection between these 2 points is given by the linear interpolation. Yeah. Okay. Okay, so we look into the AISC. So basically, what we derive, okay, basically it is the general case that you will find to make your life simple. Okay, just this one you can download the AISC 16 for free. I think I used to mention, but AISC specification 2016 available in PDF format for free. Unlike the past that to get it you got to pay like 50 or something US dollars. Now it's for free. I hope that ACI will just give things away for free like AISC soon. ACI still charge for 130 US dollars for the code. Okay, but nobody pay, right? Okay, they will get the pirate version, free download version somewhere or some source. Okay, it feels better to get the legal version for free. Anyhow, all right. There are actually like many cross section, many types. Okay, that is available for the design. The design standard provided by AISC just cover all these things. So limit state, we have the yielding. Yielding means the plastic moment, okay, development, and also the lateral torsional buckling. It is subjected to these 2. For this sort of cross section, the cross section looks like the Y flange shape and the C shape. Okay, under the condition that flange slenderness must be compact. web slenderness must be also compact. Most of the steel in the steel table, out of like so many 50, 60 or even more, I remember that just one or two are non-compact. Okay, the cross section was actually designed such that they are compact. Compact means you will not have the issue about the local failure, like the local buckling in web, local buckling in flange, okay, subjected to this loading condition. Okay, so the web thickness will be controlled, flange thickness also controlled, and with the given geometry, you can be sure that it will not just produce like web buckling, flange buckling. Okay, so as it is a commercial cross section and people tend to like it better. Okay, you can design the other cross section, of course. Right? AISC provide you the specification. The point is that it is just the mess. Okay, you have something to check. Okay, even more. Some situation that you may find, okay, this one will not be so likely then, okay, this one, okay, I doubt if this lifetime you'll be seeing this thing, okay, fine, but okay, maybe this one could be the case, right, under the minor axis, okay, bending in minor axis. The other cases will not be so likely. Anyhow, you have the tools to make use of, but just for information that in general, commercial cross section are compact, alright. But in order to check that, there will be the guideline for the check in the first or second chapters that talks about the compactness of the cross section. Okay, so if you are in the design of steel structure, you need to make your steel table, and then you can check like the compact and non-compactness, right, for each of section that you have, okay, such that you know that the formulas, okay, and recommendations, if it can be applicable to the case that you are dealing with, okay, but this case will be the general one that you are going to use, okay. So over here, yeah, initially in AISC, the first part it talks about the general provision, so that talks about the stress reduction factor or factor of safety. You have two options to do the LFD or LRFD or ASD. Okay, ASD 1.67, this is the factor of safety. In the past, it used to be like 2. Okay, but as the design and knowledge about the steel is improved, okay, the factor of safety reduced to 1.67, which is like what, 5/3 of the service load. Okay, 5/3 times of the service load. You have that much, 2/3, okay, as a safety margin. Okay. In contrast, for the LRFD, you find that LRFD isn't changing. The strength reduction factor for the beam, which is the ductile failure mode, okay, is still 0.9. The thing is that it's not changing at the strength reduction factor. Okay? You for LRFD, you have two parts. the parts that give you the safety against the imperfection of the member during the construction. So you don't expect 100% of the capacity you design. Okay, you reduce the strength. You have another part which is the load factor. Okay, the load factor is the part that magnify your load up. So you have 1.2 still for the current one. Okay, 1.2 dead load and 1.6 live load. Actually, that part of the force, okay, of the load factor, it is with the LRF, ASCE, okay, ASCE 7. Right. ASCE talks about load, ASCE 7. So if you download the ASCE 7, you find the load which is based on the American point of view. Something is applicable, something might not, okay, but that will include the load information actually quite very very good information about load. In Thai code you have the load, okay, which is like refer to the standard 30-40 years ago, okay, for the life load, okay. ASCE 7 always update, so it doesn't really just stick there like Thai code. I don't know about the other country code, but in some situation where it is like very rare, you cannot find the load in the table. Okay, it said that okay, for school, for residents, for like public area, for the car park. Car park is just so general. Car park, okay. Sometimes you have no idea, okay, if I have like a truck parking or some other kind of parking, which one should you go for? Okay, but ASCE 7 always update, and it includes like so many, okay, cases for the life load. So you will find quite a big table in ASCE 7 describing many load cases, okay, in the cinema, in kindergarten, in the high school, whatsoever. Okay, that's so many weird situations that you cannot find in the other in Thai code, okay, since ASCE 7. It's a good reference, but something you got to keep in mind that the construction in the US is different than in this Pacific region. Okay, so the US, okay, they have the different sort of load, different sort of behavior. Furniture might be different. Okay, these are the information, the statistical information collected from the usage of structure. All right, so it's statistic. Okay, it is not a rule. Okay, it is a statistic. Then the behavioral usage, okay, could be different. So in some case, you should be use it with some extra. Well, you got to consider it a little bit before you just get the number to use, and the unit will be like pound per square foot. Okay, it will be a different unit, so you need to convert it into, well, say Newton or kilogram per square meters. Okay, and then in ASCE 7, it does not include just the life load. Okay, well, you will have the dead load. Okay, you find like so many weight of materials. You will find snow load, flood load, wind load, wind and earthquake engineering. Okay, wind load. But the wind load in there, okay, they just produce like many cases. Like for example, you have the factory with a gable frame like this. Okay, windward side, leeward side. Okay, what will be the pressure on this side and on the back? Okay, they give you like a formula such that it is easy for you to design. Okay, so you just get numbers in there. So reading through a SCE 7 is actually recommended for you if you want to be the design engineer, okay, one day. Okay, read through the book. The booklet is just about this thick, okay, single page printing. So it's not like as thick as ACI, okay, it's just about this thick, okay, ASCE 7. So go through chapter by chapter. Some chapter you might not need like to snow load, okay, we will not have snow there around here. But wind, okay, might be useful for you. Earthquake code in many countries, all right, around here are having the, how to say, the foundation from ASCE 7. Well, that includes also the code for Thailand. That could be producing quite a good matching with the case for the Philippines. Myanmar should be also okay because the nature of the earthquake, okay, mainly are not like in Thailand. Thailand we have like the long distance earthquake. Okay. So the long distance one, the waveform could be different from the spectrum given in ASCE, right? But still ASCE has been used in many parts of our code. So it is like the backbone for the loads used in many situations. The flat load is also there if you want to compute and design for the flood if you are in a prone area to the flood, right? So many goodies over there. Sometimes when you are like blind, okay, maybe you have a zoo load, for example. What should be in there? I believe that they have a weird situation like that. Okay, so okay, when you are really blind and instead of using some figures that you have no idea about, at least you get something with the reference. Okay, that okay, this is recommended for use. Okay, better than like, okay, I'm gonna use 500 kilograms per square meter for some reason, I don't know. Like, yeah, for example, you talk about warehouse load. Warehouse could be varying from 500 to like 10 tons per square meter. Okay, in the recommendation, sometimes you find like 500 for kilograms for warehouse load, but oh no, generally it stacks up. And when it stacks up a lot, then you can get up to 3 tons, 5 tons. And if it is like a heavy industry warehouse, like a steel warehouse, okay, one coil of steel weigh like 5-6 tons already. So that's a bunch of load. Okay, so I think they also give like quite a precise information for you, and then you can make the choice of you can design the structure only. You know, if I ask you like, okay, if this room is to be the chiller and the cooling system is to be in this room, okay, you have no idea. The chiller system, okay, some air condensing unit or some sort of thing, okay, which is quite heavy, but you have no idea how heavy that thing is, and then 10 tons per square meter or 5 tons per square meter, you can end up with 2 totally different design from the beam depth of 1.5 meters, right? With the estimation that is like too crazy, too conservative, okay? So all right? And sometimes you are so conservative, but you're still not happy and you cannot sleep in the night because you are not still satisfied with 10 tons per square meter. Okay, so right, and that recommendation will help you. Okay, we have something over here. The CB. This is the coefficient that is used to adjust the shape of bending moment. Okay, what is this? Keep in mind that the derivation we made in the beam, okay, is exclusively for the case where the beam is subjected to uniform moment M, okay, over, okay. But in reality, you will not get this, okay. It is the, how to say, it is just used for the derivation, okay. Now, how to be conservative, okay. If you want to be conservative, actually the CB will be given as 1.0. The point is that, why is it conservative for CB equals to 1.0? The moment is uniform, okay? But the other case, when you have just the large moment in some area and then small moment in the other area, you should be having more capacity than the beam with this. So I make it like this. This is my beam. This is the moment. So this is M max. Oh, sorry. In comparison with another case, this is M max. Okay, so this case here, you will be having more capacity or the higher critical moment than this case, because for this case you are saturating the whole beam with this max moment, okay. Whereas for this, okay, on the two sides you still have like lower moment. So the effect of the lateral torsional buckling and also those warpings kind of things is less in this picture. However, if you are lazy, when you design, you can be lazy, okay? When the client give you like quite a stingy compensation, you will be lazy, okay? So, okay, this is not an ethic, right? but that's the reality, okay? Sometimes you get a design job with like a very cheap price. You will not be so, you will just make it safe, but you will not make it so economy. That's the whole thing. Like, okay, one house, you get 10,000 baht to design the structure like that. Small house, so are you going to have like 18 beams in that house? B1, B2, B3, B4, up to B18, and then you have to check the shear, check the bending, check the ductility for all beams? I don't think so. 18 beam calculation, if you divide, or not including the column, and then if you divide the 10,000 by 18, you get how much? 500 baht, probably, right, per beam. Your life is so cheap, eh? So as it is so cheap like that, okay, you have B1 and B2, and that's for the whole house. So you'll be having like quite a very overstrength beam many places, but okay, that's the deal. Okay, you just don't want to design for too many members. that's the reality. Okay. And when you graduate, you'll find that this market, okay, design, okay, to be a, well, if you are in the office, okay, big projects, right? But sometimes you are in the office and then you want to get some what, some money, huh? Okay, extra money, okay, to pay the bill at the end of the month or some other things, right? After working hours, you get some design job. Okay, you find that when you are a freelance, you are very cheap because you have like, I don't know how's about other countries, but this is a market in Thailand. When you are a freelance, you are like very cheap because you are competing with other freelancers. And the job market, design market is like brutal, and that is the important thing and dangerous thing that lower down the quality of the design in Thailand. Because you say 20,000, you say 10,000, the homeowner will just go with 10,000. Homeowner, what will be the difference? Homeowner has no idea, not educated. Well, he might provide 18B18 up to B18, okay? He might provide just B2. Homeowner has no idea. B18 and B2. Maybe getting like this thick of detailed drawing and few pages of detailed drawing. Homeowner doesn't know. Nobody aware of the value of the good engineering design, unless you are talking about a big construction project. So if you are designing like $1 billion, $1 billion baht high-rise building, okay, you compare shoulder to shoulder. Okay, this use the performance base, save the cost down, couple of 100 millions. Then you'll be valuable. Okay, value engineering, okay, all sort of things like that will be valuable at that point. But house, come on, all right? House will be like, for structure will be 1 million, okay? No more, no less, okay? Generally. Okay. So when you are in that market, you will be cheap, and right, and then you will be competing with others, and then the price will force you to do a cheap design. That's the deal. Okay, it is a tragedy, but sorry, that's how it works in the market. So I don't do the design because it is cheap. Right. And then when it is cheap, you use this. Okay. All right. As I review, like sometimes, okay, go through many cities. Actually, your beam is capable of, okay, actual this, and then many cell phone comes up. Okay, cheap design. Actually, your beam can carry more than that 1.0 times of this case. Okay, so how much is it? So this recommendation actually has been proven that it quite works very well. So in one beam, you might be having the bending moment. Okay, whatsoever how it looks like. Just a generalized one. Okay. And then the standard just recommend that you just break this beam down into 4 pieces. This is from the numerical study. So this is nothing more than curve fitting, right? This is a curve fitting. Okay. it's a curve fitting that, okay, try to come up with the best sets of parameters, not too many, not too less, that can capture the shape of the bending moment. So you break it into 4 regions: 0, L, L quarter, L half, 3/4 L. Over here, here, and here. This is MA, MB, and MC. And then over here, this is MX. Thus, if you count the factor 12.5 at the top, down here 2.5, add up with 3, 4, 3, 3, 4, 3, add up to 10, right? 10 plus 2.5, 12.5. So you are taking the max and then compare with the weight, sort of like the inverse of weight averaging. And it is a good one, okay? The CB factor has been changed many years, okay? From the very first one and change. They are sort of like stopping with this one. It is reported that this one is okay, good enough, accurate. Sometimes a little conservative, okay, but if you like that, a little conservative, that is good. Okay. Done with this? Okay. Back here. So, okay, CP is the part that you will scale over this one. Now, the part that you have the MP, okay, that's a yielding multiplied by plastic modulus sigma MC, right? That's what you know. Keep in mind that this part is the MP. MP is not affected by CB. Okay. This part here not affected by CB. Why? Let me ask you the logic why. Simple. The logic is that plastic moment is not derived based on the uniform moment assumption, right? You don't need that. So plastic moment is basically plastic moment. You just take the cross section, find the plastic modulus, multiply by U, and that's it. It has nothing to do with the shape of bending moment. So The CB is for the lateral torsional buckling. Okay. Okay. Now, you come down to the part here where you have the L subscript R. No worry, I can just cap up the pages in AISC that is relevant to this class, and send to you. Actually, you just go and Google and check for the flexure chapter and then go through. But I can just send this to you. So you have the LP, that is the part that you can develop the full plastic moment, and this is the intermediate part that you have inelastic behavior, along with the buckling. Okay, so here will be elastic. This is elastic, but you are having the inelastic buckling, but you cannot develop the full plastic moment over here, and here is like a full empty. So this zone has, like, let's say, no instability. No LTB. Okay. So here, over this zone, the nominal moment here is given as C subscript B NP minus NP minus 0.7 F Y S X was building, and then multiply by, I just put it here, this sum. Let's go. The interpretation is no CB over here. Second step. The third one here, I send this up, no worry. So the third one will be this part here, which is the F critical multiplied by Sx. Or actually it is okay. So what is the F critical? Over here. Actually, this is derived from the same derivation that we have. Okay, so it is this one. But as mentioned, equation F2-3-4 provide identical solution to the following expression. Okay, this is the expression derived. Okay, for lateral torsional buckling for doubly symmetric. section that has been presented in the past edition. So it's basically just change the way the formulation is given out. Here it is given out in the M critical. Here it gives the F critical. Alright? So they need to still be in a job. Okay? For the code writer. So that they try to change something. But it's not actually change anything. So it is just identical, exactly the same. If you prefer this one, then just go with this one. Okay, it's been changed. Now you will find the LP and LR. Okay. So the LP is the first one that controls that your column will not have any sort of lateral buckling. Okay, so it's over there. LP is the one you have over here. Okay, so this LP is what? Equals to 1.76 subscript y square root of e over fy. Fy is a u.
LP.
LP. So you have this LP over here, easy. LI is like a lot more complicated formula, but more generally for the steel design, you need to make a nice spreadsheet just one time, and then later on you just drop in figures. The most important, the most dangerous part is to drop the wrong figure in your spreadsheet. Okay, that's the thing, because you have so many numbers in there, right? So be very careful. Okay, yeah. LR. So I can just send this out to you after the class. I think I shall remember. But if I don't remember, it is easy. Page 48 in AISC 2016. You just find AISC 2016 and then you do it by yourself. Flexure, okay? Okay. All right, and some minor detail down there. CW, okay, and rectangular French, okay, IY or H0 square over 4. I don't know, maybe they hide some figure 2 somewhere in there, the CW, because they, maybe IY for them is like 2 flanges, if I'm not wrong. It is 2 flanges if they have IYH square over 4. Our definition during our derivation is that the IC we have is for individual flange, right? But here it should be like for 2 flanges, such that it will be equivalent to what you had seen at the beginning of the class, right? Over 2. This is over 4. Over 4 because this is equals to 2 times the IC we had in class derivation. Okay. So this sort of detail kind of important when you make the spreadsheet 2 times single flange or 1 flange, and then you get confused about it, and then bang 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 boom. Okay, so that's why it needs to be understood more than just go through the code and read. So some derivation is involved because of this fact. You can get things wrong easily. Okay. Let's see. I think maybe you can find okay, all right. I see this one here. Iy is the moment of inertia about the y-axis. So it is taken from the steel table. Okay, this Iy. Generally, if they don't say that it is the moment of inertia of the flange, individual flange, then this is taken from the steel table. From the steel table, the Iy includes 2 flanges, and the I contributes from the web. Web is like nothing less than 1%, so they just, okay, you can include the web. It is 0.1% or maybe smaller, okay, very small figure. Thus, this includes twice as much as if we want to be consistent, Iy of individual flange. This is from steel cross section table. So that Iy is essentially includes everything. This is their y, okay? So it's approximate because this and this are included in Iy calculation. if you want to be a little more conservative, you have the choice of CB, even more choice than the. It doesn't look so clear today. No. So this one is AISC. You also have the BS. Okay. You also have the Euro code. Alright. So you can check into all codes. Pick up 3 CB. Plug in the value and get the smallest from 3 codes. That should be also conservative. Alright. In the case where you get like very different values, like a sharp difference between 3 expressions, I think you should revisit your calculation, check again, because when you use it with just one source and then you drop in something incorrectly, all right, and then you don't know anything because there is nothing to help check. It is something that you have no clue, right? CB, what is it? 3.0, is it good? It is not tangible. 5.0? You have no idea about it, right? So providing the sort of cross-checking with the other code shall be the way. Maybe finally you end up with 1.0 because okay, if 1.0 again good for design, but when you find that your design is in trouble, when you design already, the drawing is on the construction site and constructed already, and then someone asks you, hey, I don't feel that your beam will be safe under this regard, okay, knowing this and that, then you will freaking out. You want to get the maximum capacity for your beam now, right? At this moment when the building is constructed, you are not going for CB equal to 1, you will go for CB to something to the max to check that your structure will be safe. So under that, you will need to evaluate the CB precisely. Okay. So there will be some situation you want to go for conservative, some situation you want to go for the max possible value to save to prove that you are doing things right. Okay, all right. So for the beam, okay, it's pretty much all with this. For the other cases, then you just go through AISC. Okay, formula will be adjusted, okay, in the detail, and then you can use it. The point is that I hope that you understand, okay, how things come up, okay, not just using the formula, but to use it with some good understanding. Okay. So after this point, okay, we will be talking about the tomorrow will be the brace. So we talk about the brace of the column and brace for the beam. So the beam is not actually finished yet, okay? We'll be back and we talk about the brace. So the installation of the brace to the beam matters the capacity, right? You install the brace at the top flange, you install the brace at the bottom flange, or at the web, where you have different capacity, right? And the brace design is also very important to maximize the capacity of your beam. So, okay, to tomorrow we start with the breast. We have, I think, about 8 more include today. It is like 8 more classes. So cut today out, you have 7 more classes, okay, to the final examination. Okay. So about 1 month in April, and last month of April is the final exam. So we have about that many classes. Right, so we will wrap up the breast issue. Okay, so